this November event. Today we will talk about Arduino Engineering Kit, the third project. I don't know who of you already attended the last event on Arduino Engineering Kit. There was also a rover, okay, a rover that moved on a plane last event, and a self-balancing motorbike. So it was a motorbike that with an inertial wheel, with a feedback control, was able to keep itself vertical, okay, without the help of external force. So today we will talk about this. A very short introduction for those of you that didn't know who we are. Me and Alberto, I'm Daniele. We are the Matter ambassador, so we are the link between Matters and Polytechnical from the student side. So we will help you when you want, when you need some help for your MATLAB project, or when you have some trouble with MATLAB. And we do like this event where we show you some news, some new functionalities, and so on. Only to show you what is the importance of this group, our community. I can carry you an example. For example, last week, one student of master degree in physics, I think, had some trouble with his master thesis, and it was a very helpful our different point of view, so he can solve its problem on the master thesis and go on with the thesis. So when you have some problems, some troubles, write on our groups. It's not a problem. We are there for this reason, and we will try to help you in the best way we can. Okay. So for those of you that are not on our community, please let are here so we can stay in touch. Okay, let's go with today's case study. What we will see is a short introduction. After that, we will have some hints on image analysis, because we need the image analysis in order to perform today's task. After that, a little bit of coding to show you with this image analysis function how they work. After that, the break and the real case study, so kinematic and dynamic of this small robot. The coding, we will share you. If you go on the Facebook group, there is a link to a folder. If you want to follow you as coding, let's download this folder, because you need some basis to start from. And after that, the challenge that is for the prizes. So let's start with a little bit of an introduction. What we want to do is take an image, whatever you want. In this case, the MATLAB logo. Okay. The first phase is pre-process the image to extract the border. Okay. So before the start drawing, we need to pre-process the image and extract the border that composes our image to simplify the task. Okay. So what we can obtain is something like this. As you can see, there is the principal border of our image, but also some internal borders, okay? Like this one, that is this, and this. So we simplify the image in order to obtain a path that our robot will perform, will do, in order to obtain the final image, okay? After that, the second phase is to draw this path, to follow this path with the rover, the robot, and draw the actual image. Okay, it's a very easy flow of information, but it's important. So the first part will be on this, so the pre-processing of the image. The second part will be how we can move the robot in order to draw the image. Okay, it's clear for everybody. Okay, so the first phase is image analysis. I think that most of you already know something about image analysis in MATLAB. It is very easy in this case. You have to know that the image, when you import an image in MATLAB, it is imported like a 3D matrix, okay? Each point, each element of the matrix is a pixel of the image, and it contains a number between 0 and 255. That is the quantity of that color that is present in that specific pixel, okay? So RGB are the three main components of the primary colors, of course, and the composition of these three different colors gives the last, the final result, the final color, okay? So the data type of this pixel are uint of 8, so is a 8-bit codification that gives you this information. So starting from these are some of the functions that we need in order to perform our task. Let's start from the top one. emRead is simply the function that lets you import an image in MATLAB and read this image like a matrix, the task that I told you 1 second ago. After that, the image show simply retransform the matrix form of the image into a displayeable image. So you can see, of course, you want see a matrix when you want to see an image. You want to see the real image, the final one. So em show is the function that you need. RGB to gray is, like the name states, the transformation from the RGB, so 3D matrix, to one 2D matrix. So we convert the RGB image into a grayscale image, okay? This is performed automatically. You can also state how this task is performed, so how you have to compact the color into the grayscale. But the final result is a 2D matrix with only the gray part of your image, okay? This step is fundamental because IM binarize, it is a function that gives you the possibility to transform your grayscale image into a binary image. What does it mean? It means that the grayscale image is composed from elements that goes from 0 to 155, okay? But in our case, we need the contour, the border of our image, okay? We don't need all of the different gray part of our image. We need only the border, the main border. So IM binaries transform into binary image, and so you can extract all of the pixels that are greater than some quantity will become 1, so logic value 1. The other pixel will become 0. So at the end, you obtain an image that is composed only with a border, your final border, on a black background, okay? It's clear for everybody. We will see in a moment how this task is performed. After that, if we have a binary image, we can do some trick with the black and white morph. This applies some morphological transformation to the image, the binary image, in order to obtain the final one. Okay. So now, for those of you that have downloaded the code, we can try this function together. Okay. So let's open. There is on the folder that I shared with you on the Facebook page. There is this is like quite small. Try to. Okay. There is one moment. There is this folder, this is called image. you can open this folder. Okay, there is image analysis sol is the solution file. Image analysis blank is the one that we will open now. I can delete. Okay. I can try increasing the dimension. Okay, I cannot. Preference font, modify the common window. It is a large script, but okay, I can review the code. For those of you that have the code on the code PC, it's not a problem. For the other, I will read the code. So let's start, for example, with img, so image. Img, so read, and we will read the Arduino logo, okay? Not the Arduino logo, but the Matos logo in this case. So we simply write okay, that's this. The live script gives you the results of your script. Yes. Okay, live script. The live script is not. Okay. Can you read now? Yeah. Okay. So, for example, read Matos logo. If I click run section, okay, perfect. There is no image. Perfect. Arduino logo. Okay, let's read the Arduino logo. And after that, I will simply want to show my image, so show, okay, img. If I run this section, no, cos'è adesso? Let's take another image, it's not so good one, I don't know. Because this was one image that the rover draw, okay? I take another one. Okay. Okay. Okay, so Matos logo. Same thing, run section. JPEG, yeah, thank you. Sorry guys. Okay, this is our image, okay. Show, I can show the image, and that's all. Now we can perform some modification, the function that I showed you one moment ago. So, for example, EMG2, we convert to the gray scale, RGB to gray, img. And after that, I want to simply see the results of my modification, okay? So img2. If I run this section, in this case it doesn't change so much because the image was white in the grayscale, but is changed the notation, the data type, okay? So the second transformation we can perform is IM. Okay. IM binarize. This was as I told you, the transformation that gives you the possibility to binarize the image. These are only some properties. That give you how you can transform the image from normal type to the binary one, okay? In this case, we need also this part. This is some program. Okay. And I show this image. So, yeah, show. Yeah, okay, so if I run this section now, so let's, as you can see here, I have the binary image. I have one where there are the borders, okay, and 0 for the buffer. Okay, so now I can go on and perform some other morphological transformation. For example, one is a cleanup of the image, because of course we want to avoid that the image have some part that the rover will show. So img break clean.
Excuse me.
Yeah.
What's the purpose of the tilde that you put in I'm binary?
Because you have to invert white and
okay.
Right.
It's just
Yeah,
for the question.
Yeah. Okay. So in this case, I clean up the image, and as the last transformation, I perform the thin. So I make the border thinner, okay? Because actually we don't need the border very large, because our drawing robot can draw only one single line, okay? So -5, okay. Okay, if I show off, I show the last image, the last transformation. I can run the session. Okay. This last one, this last image, is the one that we will use. It's difficult to see from the projector, but as you can see, there is the border very thin. That is our objective in order to start drawing on the border. And the image is now ready for the next task, okay? It's clear for everybody. So we take the image, grayscale, binarize it, and the morphological transformation to clean up the image and make the drawing thinner, okay? So the next step, of course, now we have an image with the border of our drawing, but we want, of course, to obtain from the image the path that the robot must perform in order to obtain an image.
So, what are the part that the tasks that we need to perform in order to get the final path? We will get the coordinates of a finite number of points inside the image. Okay. We create a segment that link discretize these points. We connect these segments, and finally, we want to convert, of course, the pixel dimension into the meters dimension, because we will draw our image in the real world. Okay. So this is the first. The first task. So get the coordinates. For this function, I cannot write the function with you because are a little bit more complicated, but we can read it together. It's quite easy. First of all, in this case, I want to get some finite point, some finite coordinates. So I take curves that I take shape image that is our image, the one that we obtained from the previous task, and I use these B view boundaries. So I find the boundaries inside the image, and I extract these boundaries inside this matrix, curves and the number of boundaries. In our case, it will obtain the boundaries of our matrix log and the inner boundaries. Okay, I want to get these boundaries. After that, simply I obtain from the cell, because this function returns a cell array, I obtain a matrix, and simply I remove all of the points duplicate, because this function can give me some duplicate point. I remove the duplicates, and I obtain the final coordinates of all of the points that I need. Okay. When I get the coordinates, I can link these coordinates to obtain the segment. Of course, the image, the real image, is very definite. In our case, we need to discretize the image in some bigger segment, because our drawing rover is not so definite. We need to, of course, obtain a finite number of segments. It's clear. So in this case, I simply take the points that are near, okay, and I link them inside this structure. So I take the 2 points near, I link them, and I say this point is correlated with this point. This is a segment, okay? This for all of the points that we have in our image. After that, what we can do is connect segments. So I take my segments and I connect them one to each other, and I convert the segment that I obtained into the matrix, the meter conversion. So I have, of course, a scale factor that I can use in order to obtain an image that is compatible with the dimension of our whiteboard. Okay, so let's do it together. You have this function, so you can see and you can check out when you want. So if I take MATLAB, we can go further. So first of all, we get the coordinates. Okay. So coordinates. I use this name only because I have already prepared the code, but you can of course use whatever you want. We get the coordinates of the last image, okay, here. So with this function, we simply get the coordinates with the function that I showed you at the moment before. If we want to see the result, we have to use a scatter plot. This is a function that transforms the coordinates, take the second row, okay, in order to plot our coordinates. It's simply a matrix, of course. Okay. first row, so x and y of our coordinates, and we want to plot them with a dot. Okay, here we can give some properties to our plot. And if you run this section, okay, what we obtain is this result. It can seem a continuous line. Actually, they are lots of coordinates, lots of points that discretize our image. Okay, here. Okay. Once we have our coordinates, we can break down our image into the segmentation. Okay, so segment x equal to coordinates to segments of coordinates x. Okay. This function take the coordinates and link them in order to obtain the final segment. Okay, now I copy only for to be faster a function that simply show you this part. Okay, if we run this section, we obtain this figure. Okay, can you see the color? The color are the different segments of our image. So we have the orange one, the blue one, and the yellow one. And this little one is violet. Okay. Same thing. We have to merge the segments. So once we have our segmentation, x, the last function is connect segments of our segment x. Okay. This will connect these segments together in order to obtain the final part of our image. So last thing, of course, the function that scale our image from the pixel to the meters measure means the limits of x and y axis of our image. We give them the limits in pixel, and it will return us the limits in meters. Okay. So in this case, we take the limits simply define watching the coordinates of our point. Okay. So mean, record, and max. Okay. Same for epsilon. I show you the final result. The final result that the merged copixel, you cannot see actually the result because it is equal to the previous one. With these two functions that are the functions that I showed you 1 month ago, we store the limits in pixel units. And finally, with these x lim and epsilon lim are the limits in meter. Okay. So we start from 10 centimeter till 80 for the x direction and 90 for the y direction. Fraction is simply a number that gives you the possibility to scale your image on the dimension of our whiteboard. And the transformation provide us the final result is that we have segments meters that are the information that we will need when we have the robot working in order to draw this pixel, this segment inside into the real world. Okay, it's clear for everyone. Okay, so now we can go on with the actual robot part. So the drawing robot. So you can see it there on the whiteboard, but let's go deeper in the detail. As you can see, it is composed by 2 motors, okay, linked with these cables to the top of the whiteboard. So these motors are DC motor with encoder, so we can know what is the position of this motor in each time instant. So we can compute actually with the mathematical computation that Albert will show you in a moment, the position on the whiteboard, provided that we know the rotation of the encoder, okay? It's clear. These are the 2 actuators for the positioning of the robot into the whiteboard. Of course, we need some other parts. The marking pen, 2 in our case, that are linked to a servo motor that is in this part, that give you the possibility to push the pen again the whiteboard or retract. Because of course, as we will see, we need to perform some segments, detach the pen, go to another position and restart the drawing. So we need this actuation, okay? This is done with the servo. This is the battery, of course, and this is the electronics. You can see in the electronics part that there are mainly 2 components. The principal one is the Arduino Maker 1000. Okay? The Arduino Maker 1000 is the little component on the top of the board, and it is quite powerful Arduino because it has DC and analog input and output, and also a Wi-Fi module. So it's particularly useful with this application, this Maker application. Okay. So these are only some specification of our board. Behind this board there is the bigger board. That is this one, the Maker motor controller. This is simply an expansion board that you can use in order to connect the 2 motors, left and right. Okay. The servo motor with this connector. All of these pins are used not only to provide the energy to the motors, but also to read the encoder. Okay. We have 2 cables for the DC, the electric, the voltage, and 5 cables for the encoder part. This is the power in from the battery, and the switch that turns on and off the robot. This is the motor and the encoder. In the first here you can see, of course, the motor, whereas this part is the encoder. Is a board with a magnet behind it that can register the position of the motor, the motor position at each time. This is the motor, and this part is only a reduction of the gearbox. Okay. So the first, of course, what we need. We don't need only image and Arduino, of course, but we need to connect MATLAB and Arduino. In our case, we will use MATLAB with a USB connection with the Arduino part. Okay, so we perform the computation on the computer online, and we send to Arduino the information on the position that Arduino actuates and draw. Okay. Okay, so now we can have a little break, and after that we will start with the second part. Okay?
Is to show you the kinematic, the dynamic of the rover and of the drawing rover, sorry, and then do a simulation all together here with the whiteboard. Okay, so let's start with the kinematic. Of course, we have this little drawing of the robot, and the first things we need to introduce is the coordinate axis. In this case, we are going to use x and y axis in this particular way. Why it's so important? Because we need to refer to the top left corner in order to move correctly the rover on the whiteboard. Because the rover, the drawing robot itself is connected on the top point of the whiteboard. So this is the most easiest way to refer the rover, the drawing robot on the whiteboard. Then we need to define the base, so the distance between the left and the right corner, in order to define one of the main coordinates of our triangle. Then we need the Z1 coordinate and then Z2 coordinate. As you can see here, we have just defined the main triangle that we are going to use to define and to move the rover, the drawing robot on the right. Now, in order to develop all the kinematic needed for this type of moving drawing robot, we need to do some step of algebra and kinematic development. So first, we need to define what is Z1, because Z1 is composed of two main parts. The part L1, that is the cable attached to the motor, that is important and that can change during the movement of the rover. And then the LR, that is fixed, and it is the distance between the center of the drawing robot, where the pencil mark is pointing on the whiteboard, and the point in which the motor is attached. Okay. So once we have defined how is composed Z1 and with what is modifiable and what is not, we can develop this, that is a simple, easy way to refer where is the drawing robot on the whiteboard using a Pythagorean law. So we can define Z1 easily as x power 2 plus y power 2, and as Z2, the complementary one. So we can combine these two formulas, okay, and get this result. Well, this result is obviously a part of the complete dynamic, because usually we want to define on the space x and y coordinate. But here we have a projection, and we need to develop it into x and y coordinate, as I said. So now with these two relations, I can say x is equal to this equation, y is equal to this equation, and we can now, once we take the output of the image analyzing part, that is a vector of point, that is xy for the first point, xy for the second point, we can convert it into z and z1 and z2. Okay, so keep in mind this formula. We will gonna code this part here and see how to implement it using the MATLAB function. So now I ask you to open the demo one empty. Of course, it's empty. So we are gonna populate the file together. Okay, you should find it into the folder drawing kinematic and dynamic. Okay. Okay. So we can start. Are you ready? Okay. First of all, as I said, we have to define the base of our whiteboard. So the distance between the two vertices of the whiteboard. So we define base equal to 60, 0.60. That is, of course, in meters. And then we define the height of our whiteboard. Now, once we have defined this, we can move on and define a function to input the length of the two coordinates, Z1 and Z2. Why it's important to define by ourselves and to put inside the code these two distances? Because let's suppose it's now we want to start the drawing rover. We don't know exactly where it's located. The rover has no feedback on how long is the two cables. So we need to measure it and put inside the code this exact distance. So I will now show you a cool way in order to get data from the user in such a way that he don't need to put it inside the terminal, the command window. So if you type str equal to input LG, you should now get with this combination. In this case, we want to put inside L1, okay, emitter. Then we want to put inside L2, again emitter. Sorry, we need the affix here, this way, again emitter. Okay, and this is the two fields that we want to populate. Then we want to put inside what is the title of this entry box. So we want to get the enter initial length. So enter the okay. At this point, we need to specify the boundaries of this input box, that is 150. Okay. Now we get something that is like, I can show you. We can run this part here and see if it works. I select it, then right click, and then evaluate section. Okay, I misspelled something. Let's see if it works. Okay, exactly. So this is the output of our comments. It's good because we now have something that the user can interact with. So you don't need to type in the command window like L1 equal to blah 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 blah. And it's more user friendly. Okay. In this case, we need to fix this. So I copy this comment here. I substitute it here only because I misspelled something. Yeah, input was spelled right. Now we can move on and then get the data from this input box, because of course he don't know exactly if you put something that is a number or something that is not. So he can easily cast this information into Arduino. So I don't know if you know what is a casting, str to demo. Okay, and it means that this command exactly does that. Take what is inside str1 and do a casting. So it take it and we try to convert it into a number. So in this case, from this point next, it is we are sure that L1 underscore yi, it's a number. The same for the L sheet. So we simply copy it, paste it, and then we can specify that is the second one. Okay, now we have the information about the length of the two ropes. So we can move on and then right here the Z1 coordinate that, as I showed you before, is the composition of L1 plus Z of R1. So we can define how long is L underscore R. That is equal to, in our case, 0.075. And then we can also define the sum of the two parameters. So Z1 underscore y, it's equal to, as I defined before, L1, okay, plus L1 we can copy it easily here and get Z2. So Z2 and L2. I forgot to put the dot comma at the end. So we have just defined how long is Z1 and Z2. Now we have all the information. What we have to do now is to define the Pythagorean law. And this is the last thing we need to do about the kinematic part. So here we can define x that is equal to open commas base, okay, at power 2 plus z1 underscore I, okay, power 2, minus here, z2 underscore I, power 2. Okay, now we have to divide it by base half this way. Okay, and we have defined x. Now, on the same way, we can define y. So y is equal to sqrt square root of z1, okay, power 2 minus x power 2. Okay, should be fine. Now, I hope you can follow me on this computation. We need to type a few seconds more. I hope it's correct. Okay. Okay. So now we can execute this code and see exactly what it does. Okay. So let's start. I use this arrow on the top here that is run and advanced. So I define what is the base. Then I run the input of the two lengths. Now I put something that is not, of course, we can measure it, or we can put something that some value, a casual value. In this case, I put 40, 0.40, and then 0.40 again. Okay. And we have created the two values. Perfect. We now can run again. Okay, we see here in the left, in the case, bottom left corner, that we step by step generate the variables. And then here we now at the last part, we can run it, and hopefully we should see here our dot on the graph. This graph, it's not the usual one. You can see here I have put this last row that specifies that the 0 point of the graph is on the top left corner. In this case, it's quite interesting because so we can see exactly how is on the correct graph the starting point. Okay, are you following it? Okay, very good. Now we can move on and go to the kinematic part, the dynamic part on the presentation. Here we are. So, speaking of kinematic, we can do a step forward on the, let's say, the modeling of our drawing rover, because exactly what we're going to introduce now is the force and the torque request to move this drawing robot on the surface. In particular, we can find this that is a simple, of course, set of force, but can be quite interesting to see how it can be modeled using math. So first of all, we need to debrief a little bit the mathematics behind this model. First of all, we have F1, but F1 is, you have to keep in mind that it is composed by the first here it's called the T1, that is the force from the fixed point up to the pulley, and then T2 that is the force that the motor applies. And this is important because F1 is equal to 2 multiplied by T1. So we have two forces that are half of the composite one. Okay. Keep this in mind. Later you will understand why it's important. Now, from the kinematic part, you have to remember that we define this as the reference coordinate plane. Okay. So we can decompose these two vectors, F1 and F2, using this projection law into the two composite, F1 sinus of V1 and then F1 cosine and so on. Why it's so important? Because we want to apply the balance of force, the Newton law. Okay, and this is important because we need to compute exactly how much is on the vertical axis and how much are the forces on the y-axis. Okay, so we can end up with this system that is, of course, the decomposition in the two y and x axis. But again, this is not very useful for our model because we don't have explicit dependency from f to some type of angle. So we need to do some computation, and we end up with this projection. This is very interesting. We have now the exact value of f1, function of the two angles, and we have the exact value of f2, function of the other two angles, so the same angle as before, as I showed here in this picture. But the problem now is that these two forces are function of angle. But as I showed you before, we don't have angles, we have x and y coordinate. So how we can compute these two angles? Again, we keep in mind our base of analysis, and we use the law of sines. And we can get this information that are the two angles function of x and z1, and then base minus x and z2. So we are, in practice, we have all the information. We need now to define our model into simuli, but keep in mind that it's the next step. Before it, we need to do a little, let's say, I have to remind you some basic of the motor, because as my colleague showed you, we have the different components here. But today, to move the drawing robot on the whiteboard, we need to attach at the end of the shaft this pulley and this cable. And they are important because if they can keep the cable, so the object that can allow the drawing robot to move on the whiteboard, keep in tension and then change the position. So we need to define exactly which is the torque that this motor can generate, because you can imagine that while you move it on the surface, it will generate some type of torque, some type of force in order to pull the drawing robot in some place. Okay. In this case, we have this formula that is quite easy. We have the voltage, some angular speed with the radius, and then we have the resistance of the motor, and then some coefficient to scale this information. Keep this as given, and this is the let's say the base of the modeling of the torque of the motor. Okay, we can now define the two extremes. So the one with the free motion. So in the case we don't have any force on the motor. And then the opposite case, that is the stall. In the case I put so much torque on the motor that it cannot spin. So the max, we can say that tau stall is the max force that he can apply. Meanwhile, the other is the velocity, and the velocity that it can reach in the case it is free of any type of external forces. Okay. And as you can show here in this picture, we can project the tau that I just defined here, okay, with this formula, with the radius of the spool, and then we can get the t. And as I defined before, t is equal to half of the force that we defined in the other equation. So, doing let's say the complex, the big picture, we have the force that we can calculate with the angles that are obtained using the kinematic mode. Okay, so kinematic mode, angles. We have computed the force we can put inside the angle, and then with this force and this relation, we can know exactly which is the torque that the motor has to generate in order to move it onto the whiteboard. So now we have all the components. We can do a little. We can get a look on the code about this. We will not write it together. It's already done. So I ask you to open MATLAB again and see this code. It should name task 4. A little comment about why it's task 4. You should find in the folder all the tasks from 1 to 7 that are all the steps that this robot comes with. So if you want to do a little more of to see more in depth the code, you can look at this script, and also there's the function. So if you want to try to replicate it at home, or I don't know, for any reason you want to see more in depth the code, it's all published to you. Okay. So let's see what this code does very quickly. The interesting part is this. So it starts by defining the voltage of the battery. Okay. And it defines the max speed that the motor can reach, and convert it into the radian on second. This is important because it's the maximum speed that the motor can reach. Then we define the opposite part, so which is the maximum torque that the motor can generate, and we can now define the two opposites. So what we're going to do now is to calculate how much of the maximum power we want to use. So this is only to calculate the motor constant, okay? And here is the part that we are going to use. So we have defined in the code above how much is tau max. And now we want to, we just defined what is how much is tau store. We want to define the maximum torque that the motor can reach as a fraction of this, in order to be sure that the motor can always move on the whiteboard. And this is in fact the step we want to perform. And this is the computation. Moving on, we want to define the dimension of the whiteboard, because it's important to say to our program how big is the whiteboard on which he has to move the So we define the age of the board, and we define we import the value of the base. So moving on, we want to define the grid of the possible position. This is important because we work on something that is discretized. We define exactly how many pointers in this whiteboard. So we take from 0 to the base dimension, and then we take from 0 to the age dimension, and we define a grid that can let's say that is represent our whiteboard. Okay, so this is mainly a grid that represents the whiteboard, and this is important because later on we want to use this grid to define on each pixel of this grid how much is the force that the robot has to generate to move on that pixel. Okay, So what I've not done until now is to execute the code step by step. So let's remember we are on the row 18. So let's move on. Sorry. Let's execute it step by step. Okay. 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 Now we are on the again. This is the position. So the same as we defined before, that are the kinematic. And then we define with the load theorem, that is the one that I just explained to you, what is theta 1 and theta 2. Then we write the force that we just computed. And then we go to the last step, that is defining the tau 1 and tau 2, that are, of course, tau 1 and tau 2 that are the half of the force multiplied by the radius of the spool. And so we have defined all the possible constant and all the possible value we need on our model. So let's run also this part of the code. Okay, now we are arriving to something that does something beautiful, show us something. So let's do it together. We can press run in advance, and we see exactly this. Okay, very good. This is exactly what I want to show you. It's a little bit okay. Okay. On this coordinate here, we start from 0 and we go up to 0.9. That is the height of our whiteboard. Okay. And here you say, and you can see from 0 to 0.6, that is the base of our whiteboard. So you may ask, what does it mean? This is on the z-axis, the force, the motor load that the drawing robot has to deal with. So on the bottom corner of the whiteboard, you can easily see and think that you have the two pulley, the two cables that are really long. So let's say the V that they form to the base is very narrow. So you don't have to put a lot of force, because all the mass of the rover is well defined on the two cables. Instead, if it goes up to the top, the two cable, the V is very large, so it has to generate a lot of power to move on the top corner. So we wanna define now is to move on and define which are the area that he has to move into. In this case, this is the projection on that. So if you look at that graph on the top, you will see this let's say this representation. But I suppose that this is the one that we want, because as you can see here, this is the rectangle in which our drawing robot will move, and it will do the drawing, because as you can see, it's all of the same color. So once he decides which is the force that he has to apply, he can move on all this part in a way that is more or less the same. Okay, so this is our last step in order to define exactly where the rover can move. So this last line is to save it into a into a matrix, in order to then use in another script to decide where the drawing robot can move. Now, about the kinematics and the dynamic, we are at the end. What I can suggest now is to move here with the okay. We can do it this way. Sorry. Meanwhile, I connect my PC to the drawing robot in order to show you a real demo that we can do later on. I ask you to, if you want to win some prize or to get some prize, to log in and to go to the soccerkid.com website. We are